document. And okay, so I am a mechanical and software engineer specialized in computer simulation for a long time. I worked in a lot of different industries, doing a lot of different target applications and uses in a lot of different architectural considerations. By the way, these slides are on my website at the link at the bottom. And
It's
they're
also
right
in the
here
chat.
live in the reveal.js framework, so they're always online, they're always interactive. It's a one-page web application, and the links go to other presentations, other slide decks, blog posts, articles, and other source materials. So that'll be there for you. So the first examples of links in the presentation are these two in orange here, applications and architecture. If you happen to be interested, here are graphic representations of work I've done for continuous simulation of the heating inside of a steel workpiece that's going to be rolled in a discrete event simulation of some random process. That framework was written in JavaScript, by the way, so that's live elsewhere on my website. So, when I read my final college newspaper, there was a magazine insert in there. And there was an article that I remember that said, your first job won't be your dream job. I mean, it might be, but it's probably not going to be. Your goal is to just go out and get your first job and see what happens from there. So I knew I wanted to be an engineer and I wanted to work with computers. I didn't know how I'd integrate those, but I got lucky. There's another link, and I loved it right from the beginning. And I kept bouncing around to different companies, different locations, different industries, and never became great at industry knowledge in any one area. But I ended up becoming pretty great, I think, at the meta, which is what skills in analytical tools apply across all of those different situations. So, one of the other things you have to be aware of uh, in school, when you get problems to solve, they're relatively contrived, they omit a lot of complication. There's a classic early physics problem you may recognize it. Um, and it basically asks you to balance certain forces and whatever. But the basic form of this problem omits all the complications. Um, the static friction before the piece on the inclined plane stops or starts moving, and any complication having to do with that string going over the pulley and the pulley. So you don't think about the friction in the string, in the pulley, or anything else. You don't think about the string stretching. You don't think about the mass, because as those things move, the weight on either side of the pulley changes and the problem gets a lot more complex. In the real world, you may have to do that. My high school physics teacher always joked that string connecting the masses is a massless, frictionless, non-elastic, but perfectly flexible physics connecting device. Sometimes you can assume that, but sometimes you can't. If you imagine the anchor chain on an aircraft carrier, it's big, ugly, loud, frictiony, and so on, and it certainly has a lot of weight to it. So the real world, you're going to have to deal with everything. And if you don't deal with it in your early jobs, you will certainly do so in your later ones. One of the important things is to always look under the hood. You want to know more about what's going on at all times. You can't be expected to know it all right away, but you have to start. You start in a limited place and you'll grow from there. Oh, overall, I want to share with you some insights that I've learned that I kind of wish I knew when I was your age. Now, I don't know if I would have been able to make use of it directly, but um, my real goal is 5 or 10 years down the road, you'll say, I get that context. That strange guy who can't talk all that well was telling me, and now I know what to look for. So that's kind of my goal. So if you're starting to, say, learn to program, you just don't really think about a lot of details. Just kind of start in the middle of this stack. And the programming language, um, you just kind of live within the world that it presents to you. You get the kind of variables and structures and actions and formats that it gives you, and you don't think about lower level details or higher level details to start. So there are zillions of programming languages out there. I've worked with about 20, and you get down to assembly and language in the operating system, the BIOS, which is the operating system on the hardware, the processor, the individual units within that, and the physical logic gates. You don't know all that stuff, and you don't necessarily need to know the whole stack, but you need to, the more you know about some of that stuff going down, the better off you're going to be. And then going up, once you do communication and IO and system architecture and enterprise architecture, that's a whole nother universe of complexity you'll have to figure out. So you'll start in one limited place in all of these contexts that I'm going to describe, and you'll branch out from there. So I want to talk about four major contexts: the process, the engagement, the solution, and the environment. Because we're talking about the life cycle today, I'm going to spend most of the time talking about the engagement and what are all these things. The process is the series of steps you take to do anything. And once you get into manufacturing processes, or software logic diagrams and flowcharts and so on. That's your process. And it has all kinds of parts and components and so on we'll get into. The engagement is the structured work and phases you work with the other people through to get the work done. The solution is the change you make, either building something or changing something that already exists, and the environment is the place where you do it all. So we'll go into that too. And obviously, occasionally there'll be a link down here to other material. So the process, no matter what industry you're in, has a lot of standard components. They may look different. So a process block will look different in the paper industry. We had screens, cleaners, refiners, rotary disc filters, pipes, liquid phase separators, conveyors, all kinds of crazy stuff. And obviously, we had queues. And if you think about items going through an assembly line, then you have an entry and exit, and the entity moves through different steps. And you can do transformations, merges, splits, and so on of the entity. You'll wait in queues, you'll get routed to different places based on options or results. You can analyze the action of a machine in terms of various kinds of data. So data related to the entity and also data related to the machine. Once you're, the way you think about hooking all these things up, there's a standard analysis or what's it called? An acronym called SIPOC, which is source, input, process, output, customer. So the process is the individual thing you're thinking about, and that's one of those process blocks that are usually read on this diagram. So you think about that, you think about what comes into it and who gave it to you, or what other process or external source gave it to you. And then there can be multiple inputs and outputs. And the output is the thing you spit out and you send that to some destination. When you're analyzing things that already exist, you start with the source generally and move forward. But when you're designing for a result, you typically start from an end process and work backwards. So that's where Copus comes from. It's just SIPOC backward. And inside a process block, there are all kinds of things that can be happening: logging messages, splits, transforms, merges, waiting for things to happen. I spent a lot of time doing real-time systems and simulations of various kinds. I did all this stuff. And I can talk forever about this and many other subjects. I'll just tell you that this exists so you can keep that in your toolbox. Now we'll talk about the engagement. If we're going to get together to do work, we're going to have to identify what we're going to do and why we're going to do it. Then we have to do some kind of planning. Then we have to figure out what's going on now, if there is something going on now. If we're building new, we'll do this later. Then we'll do requirements. There are two kinds of requirements. Functional is what the thing's gonna do, and non-functional is what characteristics it's gonna have or what it is. Then we're going to do a design. It's a proposed detailed to be state. The requirements are abstract. The design is more firm. It's more less abstract. Then we actually implement it, which means build and potentially deploy. Then we do tests. There are two kinds of tests. Verification is, did the thing we built work the way we intended it to? And validation is the thing we built that we know works the way we want, does that actually solve the right problem? So there are two different kinds of tests. The first one, verification, is more automatable, but off we go. Then we'll accept it, and then we'll wrap everything up. Now, there are a couple of things that happen all the way through this. You're always dealing about assumptions, simplifications, capabilities, limitations, and risks and impacts. That goes on through all these phases, and you're always dealing with data in a lot of different contexts. So if I were to streamline that and just stick with the most important sections, I strip it down to these 7, and I'm actually gonna cut out the data, fold it in later, and I'll show you why I do that. So the intended use is, what's this thing for? The conceptual model is what's going on now. Requirements are, what do we need? Design is, how are we going to do it? Then we do it in the implementation, and we test in test. So it gets simple. Now, in order to work together as a team, we have to communicate with each other. And the field of communication is always complex. There are psychologists and signal processing experts and all kinds of theorists that think about this ad nauseum. This is the model I learned in the Army, and there are different ways to approach it. It's not a simple problem. So because it is not simple, what is a major thing we can do to make communications better and more robust? and that is we can have a conversation. So if you can imagine a conversation is a circle, we're kind of going around the green circle counterclockwise, and we enter this conversation from the yellow in the lower left. And if we want to move forward, we'll go out the green arrow in the lower right. If we want to go back to a previous conversation, we can go out the arrow in the upper left. And if we want to come back and revisit this conversation from a future one, we can come in at the blue arrow from the upper right. And what's going on there is really going back and forth until we have reached full agreement is the way we make robust conversations. In communications, you're not going to get it usually on the first try. Um, Eventually, you may have to cut it off and just move forward because you can't spend all day hashing stuff out. Like I said, you can go back and sort stuff out when you know more or things change. And I show things as a loop and explain the rest of it. So let's look at those 6 major phases as a series of conversation. So we iterate within each phase, and we can also iterate back and forth between phases. So that's all this thing is showing you. And when you do any limited piece of work that reaches some kind of conclusion, this is how I think about what people do. And there are a lot of variations on this. Um, um, yeah, I'll get to that. But if you think about iterating between phases. I mean, if you're doing conceptual modeling, you do discovery and data collection to find out what's going on now. You'll do the first pass to document it. You'll have your customer review it, and they'll say, okay, you got this wrong. You'll update it, change it, document it again, and keep reviewing until you understand. Then you can move forward. Well, think about implementation and test. When you're building software or anything else, that's the classic thing. You build it, you test it. If it passes, you're done. If it doesn't pass, you modify, and that goes back and forth. And I'll show that to you in another way shortly. Just so you know, every phase it can be very complex. The planning can involve project management, business analysis, a design analysis, and so on. And you have to do a project close. The design and implementation all had different steps. The conceptual model has different phases to it. You collect the nouns and verbs in discovery to find out what's there and what actions are happening, and then you characterize those by doing data collection. So when we have all these states or all these phases where we're doing things, they happen in a bunch of different ways. So in waterfall, in theory, you do all those things right in order, right? But I never worked on any project where you just march through all the phases and skip and tralla, we were all done. There's always iteration between phases. Now, if you're doing Agile and Scrum, you're doing the first three phases cyclically to generate a backlog, and then you groom that backlog, you prioritize things, and then the implementers actually pick items up, do design, implementation, and test. It's all the same activities in each phase, but it gives you an idea of what people are involved in, how things are arranged. If you do a hybrid of that, you might do an overarching design where you know roughly what's going to happen overall, but then you do the implementation kind of like Scrum. And if you're building a simulation to help with design requirements, implementation, and so on, that's a separate independent project embedded in the overall effort. If you're improving an existing product, you do the conceptual modeling early on, so that's where discovery and data collection is done to find out what's going on now. If you're doing something new, you're building it from the first time, there's nothing that you're going to modify. You figure out what you need first, and then the conceptual model is, hey, what are all the pieces I can use in the design I'm gonna put together? So there are always little twists on this. And finally, in order to keep it all straight, we do requirements traceability. That means we march through the phases. We start from the intended uses. Why are we doing this? And everything we do should map in both directions until we get to the end. So there's two ways to do traceability. One is across the phases, and one is hierarchically in the logical design. So imagine an airplane has an airframe and landing gear and engines and electronics and passenger comfort and luggage handling. All those are different systems. They all have subcomponents and so on. And they should match at the design phases. What's going on at the bottom is there might be requirements for how you do activities in every phase. So once you build the initial system, and that's the red through purple loops, right? Then you start using it, and that's now we're getting into the full life cycle. Every modification you do when you're actually using the system and maintaining it and so on is basically its own new engagement. And then finally, when the system is no longer usable for whatever reason, then you do an end of life. So that's the extended life cycle. And when we're talking about your career, depending on what your specialty is, you'll typically start in one or two of these circles and you'll branch out from there. So if you're a software engineer, you'll probably start in implementation, you might start in test, If you're a business person or whatever, you might be in intended use. You might be in conceptual model on discovery data collection requirements. You want people end up in one place. So you'll specialize and eventually you'll branch out to understand the entire life cycle. But as always, you'll start small and expand your knowledge. If you notice this engagement that I show is basically the SDLC. Um, the implementation is broken down into development and implementation, which is essentially deployment. They throw in a planning state or phase, but it's kind of inherent in mine. The upper one is mine, the lower one is the standard with the SDLC phases. And if you haven't heard of that, that's the software development life cycle. So the one thing you want to know about doing an engagement, and that should be engagement, not the process. I'll fix that. Is you need to know what all these parts are before you start. You don't want to launch into this and only get think about how to do testing when you get to test. You want to know what's coming. You want to start planning at the beginning and have the testers work almost from the beginning of the project creating tests. You want to know from the point of view of a project manager, you're going to need time and resources for that and so on. So now let's talk about the solution. There are a lot of ways to do solutions. There are reactive approaches, that's in the upper left, imposed by competition. So if you're other competitors are cleaning or clock, you have to respond. If your system goes to end of life, you have to do something. There are also regulations, legal actions, and so on. There are a lot of proactive things you could do. And I list a lot of those. I describe those at the link. And those are when people talk about continuous improvement, that means they're always revisiting everything they do in terms of all of those proactive approaches and looking for ways to do things better. They don't wait for somebody else to pull ahead. They're always thinking about how to apply everything they learn. These are the ways I'm aware of. If you know more, I'd love to hear about it. Again, there's a link where I have a number of short presentations across the link that describe what all these are. And there are some considerations that change how you're going to do things. I've already spoken of building versus modifying. One thing is if I'm going to make small incremental improvements, or if I'm going to make some big quantum leap and do everything totally differently, which might be a lot better. So think about, say, 3D printing or additive manufacturing versus a whole lot of make a big block of metal and start doing stuff to it. might be way different. One thing you always have to think about is the concept of trade-offs. Those of you who are familiar with code might ask, okay, is it better to run faster or use less memory? And A, the answer is it depends. But B, it's also true that there are a lot of things you may have to optimize on, and these all had to be traded off. So if you remember that early slide where I talked about the existence of many different computer languages, they all make these trade-offs ahead of time for you. So in C++, they might define 20 different kinds of numbers, but there are other, and they're all different sizes, formats, uses, memory consumption, kinds of numbers they could represent, and so on. And you have to choose them and understand what you're doing. A language like JavaScript just gives you number, gives you one numeric type that simplifies things, but what you're giving up is um, memory usage, and you're giving up control, but you're getting simplicity and hopefully maintainability. So those are the things. There's technical stuff in the computing column. You have to figure out what resources you're going to use to develop and maintain stuff in the middle column, and there's the actual cost in the rightmost column. So the ultimate optimization is you want to minimize the total cost of ownership over the entire life cycle. That's a critical thing to understand, and it's a hard thing to really get your head around. But professional managers will get this. And then the environment is okay. If we create the correct environment, we can do the best work. And that'll get people in and up to speed. It'll support the right kind of communications. Management will be done by people who actually understand the various techniques. So when you first learn something, even management, it's kind of surface at the beginning. You ultimately want to know what's really, again, under the hood. You want to have active communities of practice where people are having brown bags and working together to share knowledge. And you want to, this one's important to me. The most important thing about a work environment isn't having a foosball table so people can talk or cool snacks. It's having an environment where the work is the important thing and people can do it. That's the main thing. There are other things too. Like I said about the management practices, there were a ton of ITIL. There was Agile, Scrum, Kanban, and so on. And you have to remember that what's written isn't necessarily the way you do it. A lot of people don't understand Agile. There was a guy that helped write the Agile Manifesto. He gave a speech about 10 years ago because old Agile is dead. And the point is that don't worry about the craft and the certifications. In reality, all Agile is talking to each other. It's about this frequent communication, so you're always on the same sheet of music. Like, you don't figure out what you're gonna do, all go off for a year and do different things and come back together and try to stick the pieces together and find they don't fit. If you're communicating continuously during that time, then you'll work all those problems out interactively and incrementally so you never get too far off target. The Wikipedia article for every practice it seems to include a section for criticism, and that basically talks about this. Can do, it's not about what's formally written, it's about what that the isness of each practice if you really understand it. Finally, every technology has a life cycle. So, thinking about it from the technology side, somebody figures stuff out. Early adopters use expensive, clunky versions. They pay a lot for it. Then initial seed money allows further research, and then it kind of goes mainstream. There's broader adoptions, and then people say this is the greatest thing since sliced bread, and now we're all going to do it, and we're going to. It's the answer to every problem. Like Pedro said in Napoleon Dynamite, it'll make all your dreams come true, except it doesn't. What they eventually find is that it really makes a nice advance in a few limited areas, and then it's an incremental advance more generally, and it doesn't work in some other areas. And then the thing kind of settles down and becomes just the way people do things. It's background noise, and then the next big thing happens. That's been going on forever. If you look at the same goings on in at a company or industry level, a few people do it and then more, and then way too many people pile in, and there are zillions of companies and they're all trying different things, and then a lot of them go out of business, and then the technology is commodifying the number of organizations that do it reaches a small equilibrium, and even that may go away. I mean, this has happened with every industry on list of munch. It's happening with AI right now. It's going to be really good for some uses, incremental advance for others. A lot of companies are spending money and getting bupkis for return right now. So there's nothing different under the sun. You're living in a giant bubble. It'll be useful, but the point is that you always want to keep learning, because what's important and popular today might not be tomorrow. There is always something new going on, and you never stop learning. You never stop communicating. You start off knowing a few things, you learn more in every direction. So that's what it's about. And all those things happen in every industry. There's always industry specific knowledge. So that's important to learn. And again, thank you for letting me address you. I think that I'm grateful for the opportunity because every time I revisit this material, especially when I have a slightly different charter each time, I learn something, I make it better. So thank you. If you have any questions, hit me.
Great. Thank you very much, Bob. And please join me in thanking Bob for his time. As he mentioned, you're welcome to come off mute or post in the chat, or we also have the Q&A if you have any questions you would like to ask. And we do have some questions that were received prior, but we want to put preference for those who are here today.
Hi, I have a quick question. First of all, thank you so much for your time and for your presentation. It was awesome. I'm curious what you think about, because definitely these things, the hot topics come in waves. I'm curious if you think it's important for someone who's more in the beginner stages of learning to code and to program to start from scratch, or should they kind of use these tools, these AI tools, like ChatGPT and stuff to kind of do the basic standard coding procedures for them and kind of, learn from there and kind of like skip the beginning step, if you will. Curious your thoughts on
Um,
that.
Well, I'll tell you an exact story that is analogous to that. So I did swing dancing for 16 years before my nervous system fell apart and I couldn't anymore. And you can get to be pretty good. The problem is most of us amateurs go in and do dances on top of a foundation of not really being able to dance that well. You can't turn, you don't necessarily how to flow all your body parts the way you want. Things you learn in basic ballet and modern dance technique classes. So it's built on a foundation of uh, dancing without really knowing or how to do dances without really knowing how to dance. And there's only so good you can get. The people who do my favorite dances super well are real life, honest to God, trained from the Zygote professional dancers. They're amazing. And so I would say there is ultimately no substitute for learning what's going on under the hood. You also cannot ultimately learn uh, what the AI is doing unless you know what it should be doing. Half of the work, if you use AI to generate code, is going back and reverse engineering it to figure out what's going on. So, how's that for an answer?
Amazing. Thank you so much.
Ultimately, I would say it's always your responsibility to really know things. As a senior practitioner in all these areas, I think a lot of what AI does is, okay, people say it's eliminating junior roles. Um, because it's doing a lot of the grunt work for you. But unless you have people learning that stuff from the ground up through raw experience on their own, doing it the hard way, eventually you're gonna run out of senior practitioners who've been there and done that, know what the AI is doing. So I think AI is a nice tool. It can make some things better, some things it's amazing for, but some things there is no substitute for the personal responsibility of really understanding what should be happening. If you've ever seen the classic Star Trek two-part episode, The Menagerie, the residents of Talos 4 had their whole society go to pot because they were so busy living in their illusions, they forgot how to do their own stuff. So that's an artistic cautionary tale for you.
So we have two questions that came in. We'll start with Thea. She has her hand up, and then we'll go to chat for Amanda's.
Thank you. I wanted to expound on something Bob said, Justin. Whenever you produce a piece of work and people ask you questions about it, you're obligated to understand what it is that you produced. And whenever you use AI to do it, you created it, but you don't understand it. You might not even gone through it deeply enough to be able to explain it to someone. If you get to the point where you have to make changes to it, edits to it yourself, you don't know how it was created if you had AI do it. So you can't make the changes. It's like taking somebody else's work to be your own. And it puts you in a very awkward situation. We're going to have 1 million people that use AI to do task A, and very few of them are going to understand actually how to do that task. If you're one of the people that know how to do it and understand the guts behind it, even if you use AI to do it occasionally, you're going to be one of the leaders in the organization to make changes, to own things, to be able to explain things. Using AI can rob you if you use it improperly, but it's a very valuable tool. Just you got to know what you're doing too.
And Armando had shared a question, and as of note, people are paying attention that outside of the questions, we probably did not hear the word AI at all during Bob's session. He did give us a warning on that. A lot of that concept is that, through the years of experience, a lot of new technologies come and go and grow, and some continue moving forward, some don't. These are kind of when we talk about AI, we're talking about any kind of new concept, new project. Next year it might be a completely new acronym that we follow. But the question coming from the chat is, what are the major reasons AI projects stall or fail in your organization, or that you have seen from your experiences with new technology?
Well, I've actually been reading about this, updating my Agile certifications now, and I'm collecting SEUs for it, and they talk a lot about that. Basically, the problem is, most reasons projects fail is because people don't communicate well enough. That's A. I've also heard it expressed as poor team dynamics. It's still true that when you're doing a transformation project, 70% of projects still fail. And almost all of that, some things are just hard. Sometimes you don't have the resources, but most of all, people aren't organized and clear, and they don't communicate well enough. That's most of it. As far as the AI projects, all those things you listed, the data, the training, the infrastructure, the code, the type, the tool, the cost, all those are reasons things can fail. They're probably all about the same. And every one of those is mitigated by enhanced communication. So you have to really understand how those things should be done. Take classes, read, participate in internet forums, do community as a practice. There was tons of material on Udemy. I highly recommend data science tools of the Super Data Science Group headed by Kirill Eremenko. So it's all good stuff. There is always more to learn. By the way, I linked to it indirectly, but I didn't show you. This book, Facts and Fallacies of Software Engineering by Robert L. Glass, talks about the technology arc. And it was a really good thing to understand. Everything that was old is new again. Computing industry has been going through the same cycles of complexity and centralization and dispersion and back and so on since its inception. So really what it's really about managing complexity at the end, understanding the problem and using the latest tools to solve it. So that part's never going to change. And that goes back like 75, 80 years now.
Awesome. Well, we are right up at time here, and really appreciate everyone joining today and the questions. Bob has been gracious to share the link to his slides. I'll also share out the link with the recording, but also has provided his contact information and LinkedIn. More welcome to reach out and continue the conversation there. But we're really appreciative of your time, Bob, and the amount of information and resources you shared with us today. Thank you all. And our next virtual live session is actually tomorrow on data interoperability and enterprise learning systems. So something that's becoming a broader topic is about how you can engage with data across different systems, different platforms, and utilize them for different use cases. But have a great evening and see you all next time. Take care. Bye, everyone.